All right, gang, about 5,500. Going to transition into probably my favorite part of the class, matrices, not necessarily that we're going to study matrices, but matrices as they apply to simple linear regression. If we were going to write a program or we're going to, for the most part, calculate estimates, we're going to use matrix operations. So, we've looked at other ways, MLEs, we've looked at least squares, we've looked at obviously using R. We have formulas where we can create estimates for beta 1 and beta 0. But again, the standard approach to calculating coefficient estimates is to use matrix operations. So over the next 1, 2, 3 videos, I'm not really sure. I'm trying to keep the videos around 15 to 20 minutes. So we'll see how far we get in each one. And I'm going to gloss over a lot of the review of matrices, so it'll go pretty quickly. So again, over the next 1, 2, 3 videos, however many, we're going to review, again, briefly matrices. We're going to be introduced to how we manipulate specific to performing operations on matrices in R. That's kind of cool stuff. And we're going to look at the role of matrices in regression. So I'm pretty sure this will be divided into at least two videos. All right, taking you way back when, probably back in your undergraduate. What's a matrix? I always think of a matrix as it's a collection of objects, elements, dogs, cats, trees, data, whatever it may be, that are arranged in an array of m rows by n columns. So I've given dead easy for you to say. I have given you an example of a 2 by 3 matrix because it has two rows and it has 3 columns. Just an FYI, if we have a matrix that is, say, an n by 1 matrix, we refer to that as a column vector. If we have a 1 by n matrix, then we call that a row vector. So an example of a column vector probably goes without saying, but let's just do it anyway. Column vector, row vector. So this would be a 3 by 1. This would be obviously a 1 by 3. Now, to add and subtract multiply matrices, we have to have the same size matrix. I don't get into that much because in terms of matrix operations for simple linear regression, which is where we're headed and why we're building this, the three things that we work with the most are the product of matrices, the inverse, and the transpose. So multiplying matrices, just as an example or just as a review, I've created 2 matrices here. The first thing, if we're going to multiply 2 matrices, is we have to make sure that they can be multiplied. The way I do this is I look at the size of A, which is a 3 by 2. I look at the size of B, which is a 2 by 2. If the number of columns for the first matrix is the same as the number of rows for the second matrix, then we can multiply. The product exists. This number and this number creates the size of the product matrix. All right, so I know I'm going to have a 3 by 2 matrix when I multiply these two together. Now, the way I create these entries is, for example, this entry right here, I'm going to take a linear combination of the rows and the columns. So row 1 is 1 and 2, column 1 is negative 1 and 1. So I'm going to multiply these two values, and then I'm going to add the product of those two, row 1 with column 1. That's the way that entry is defined. This entry, on the other hand, looks at the linear combination of row 2 with column 2. So if I look at row 2 with column 2, I have 3 times 2 is 6, and I have 0 times 0 is 0. So 6 plus 0 gives me 6 for that entry. Not really sure what these others are. You can create those and go for it. And what we may do, we may just use it as an example in R. I don't know what we're going to do. Now, just an example here. Notice that B, the product of B and A, I'm trying to get rid of all my paper. I don't want too much clutter on my desk. Notice that B times A does not exist because B is a 2 by 2, A is a 3 by 2. The number of columns for the first matrix doesn't equal the number of rows for the second matrix, so the product does not exist. And I already put that right there, so that was redundant. All right, let's create some matrices. Let's transition into R. And let's just enter a few matrices. So let's enter a matrix A. Let's just do 1, 2, 3, -4. I don't know. Let's create matrix B, which would be, let's just have a row vector. And let's create a column vector of 3, -7. So let's escape out of this. Go to R. And let me demonstrate how we manipulate or create matrices in R. So the first, for A, what I would do, and this is just one approach, I'm going to show you many, to create A is I would put the elements in lowercase a. I always create my, or at least I name my matrices a capital letter when I create them in R. So I'm going to use the matrix command. The first thing I'm going to do is tell R where my entries are. So I want them to, R to look at A. The next thing I'll do is tell the number of rows. Well, in this case, I want 2 rows. Next thing I want are the number of columns. I want 2. And then I tell R how I want it to read the data. Well, when it reads 1, 2, 3, -4, I want it to insert by row. So therefore, I do by row equal true. So when I get A, you can see that I get the, you know what, I think this this actually may be helpful to do a split screen. So let's do that. All right. So B, I'm going to take a little different approach here. I'm just going to, when I have a very small matrix, I can just enter the data there. So I can see that I need 1 row, and I need 3 columns. And by row here is going to be equal to true. Actually, all I have to do is just put the capital T, and life is good. So I get a 1, 2, 7. It should be pretty clear now to create the C matrix. So I have 2 rows, 1 column, and by row equals true. So I see C, and I get this. Now, let's say, for example, I want to multiply A by C. So first of all, I would check, does the product exist? So I have a 2 by 1, or a 2 by 2 and a 2 by 1. Number of rows, number of columns of the first is equal to the number of rows of the second. So I am expecting a 2 by 1 matrix. Now, this first entry is going to be the linear combination of row 1, column 1. So I get 3 times 1 plus -7 times 2. And if my mental arithmetic is correct, that should be -11. The next thing I would do is row 2, column 1. So 3 times 3 is 9, plus 28 is 37. All right, so I put this as you would think I would do. You would think that I would just multiply A times C, right? Well, this isn't going to work, because if we multiply A times C in R, it treats it as if we're multiplying or adding the corresponding parts. The way we multiply, or, I'm sorry, the way we add matrices is, the way we add matrices is we would add the upper left component with the upper left component of the second matrices, and that would be the upper left component of the sum of the two matrices. Add the upper right with the upper right to get the upper right, and so on and so forth. Well, that's what R sees when we have an A times C. It's going to multiply the parts in the corresponding position. So to multiply matrices in R, we use A parentheses, multiplication sign, parentheses C. So in this case, we get the product negative 1137, just as we were supposed to get. So really, really easy stuff. Now, if we're going to take the inverse of a matrix, now, you guys recall the inverse of a square matrix. Now, what's a square matrix? Just means that the number of rows is equal to the number of columns. So the inverse of a square matrix A, which is denoted as A inverse, gives the identity matrix. So if we have a 2 by 2, when we multiply these two matrices together, we are going to expect to get the identity matrix 1001. To get an identity matrix in R, now since A is square, 2 by 2, we can find the inverse. And the way we do that is just use solve A. It's kind of strange, right? Not intuitively clear. But if we do solve A, and let me just create A inverse here so I can multiply those together. We can do that. So if I take A times A inverse, I am going to get the identity matrix. Now, this entry right here is a little wacky, but with the numerical techniques going on behind the scenes, that's seen as a 0, and this is just a wacky looking 1. Now, I don't know why they don't just give a 0 and 1. It has something to do with the numerical calculations behind the scenes. Next thing, transpose. So if A is equal to 1, 2, 3, 4, 5, 6, then A transpose would be equal to 1, 2, 3, 4, 5, 6. So it takes the rows and makes them columns, and it takes the columns, it takes the rows and it makes them columns. So if I want to find the transpose of A, I just use T parentheses A. So you can see what it did with our original A is we just, again, took the row, made it a column, and pretty easy stuff. All right. Now, Went through that pretty quickly because of the level of this class. Just want to, again, just give a little, about a 10-minute review. Let's actually move into matrices for regression. And I got to tell you, this is, it's not that I don't really like the previous material, but this is by far, I think, my favorite content of the class. We're not going to need R for a while, so let's just get out of it and go over here. So for matrices for regression, we can think about, first of all, we collect data. So we have n data points, x1, y1, x2, y2, and so on and so forth. First thing we can do is we can define what we call our response vector. And our response vector is just a column vector of our y's. So this value, all the way up to this value. Now, the next thing we want to look at is our design matrix X. Now, recall that our y value is equal to the expected value for y plus the error term. All right, so what we have is we have each of these values. So again, let's say that we have y equals beta 0 plus beta 1 x sub I plus an error term. So for the very first entry, we're going to have a y1 equals beta 0 plus beta 1 x term plus its own error term. We're going to have for the second term a beta 0 plus beta 1 x2 plus its own error term. We're going to repeat that down to where, for the nth term. Now, if I can think about creating a matrix for this, a matrix for this, and a matrix for this, what I actually have is I have my y vector, my response vector, times my design matrix, sort of. Let's just leave this yet to be explored, okay? Forget that. I don't know why I put that up there. So let's dive in and explore this a little bit more. So this matrix right here, what's really going on with that matrix? Well, daggone it, I didn't mean to put that. I meant to put this right here. Ignore that stuff right there. Well, what's really going on right here is the product of two matrices. Now, this is the reason that I reviewed a little bit multiplying by matrices, because to understand why this product is equivalent to this, we have to think about the way matrices are actually created. Again, here we have what? We have an n by 2, and here we have a 2 by 1. The number of columns of the first and the number of rows of the second are equal. So the product matrix is going to be an n by 1. One column, row 1, row 2, down to the nth row. Well, how do we get this element? We take a linear combination of row 1, column 1. So taking row 1, I get 1 times B0 plus B1 times X1. So 1 times B0. Does that look familiar? Well, yeah, it's exactly the very first entry in this up here. All right, so going back to this, what do we really have? Well, we have again, let's call this right here an X. Let's call this, let's just call it a beta matrix. And again, this part is taking over the part where we have so we know that this part right here is our response vector. We know that this part can be rewritten as x times beta, again, for what we saw right here. And we have our error term. So what, again, response vector? Error vector. And what happens here? We have our X and we have our beta matrix. This is called our design matrix. And this is called our coefficient vector. This becomes extremely handy when we get into multiple regression, where the the least squares approach the maximum likelihood estimation. Some of the calculations for beta 0, beta 1 get extremely messy because we have multiple predictors. This process, I hate to get too dramatic, but it just kind of saves the day. I'll tell you what, I think I'm going to end there, and we'll go further in the next video. Take care.